Bismillahirrahmanirrahim. In this lecture, we are solving problem 4.25 from Applied Thermodynamics by McConkey. So, problem statement is steam enters a turbine at 70 bar and 500 degrees centigrade. So, in given data, the initial pressure in the turbine P1 is equal to 70 bar and T1 is equal to 500 degree centigrade and leaves at 2 bar. Final pressure P2 is 2 bar at dry saturated state. Final state of the steam is final state of the steam is dry saturated. Calculate the isentropic efficiency and the effectiveness of the process. These things are required: isentropic efficiency and effectiveness. Neglect the changes of kinetic and potential energy. It means that change in kinetic energy is equal to 0 and change in potential energy is equal to 0. And assume the process is adiabatic. Adiabatic means that no heat are gained by the system and entropy will be constant. A diabatic process is also isentropic process. Required things are isentropic efficiency, and second, effectiveness of the system. We have to find isentropic efficiency and effectiveness. So in solution, first we draw TS diagram for the system. So first we check state 1. State 1, at state 1 pressure is 70 bar and temperature is 500 degrees centigrade. So first we check at this state the steam is superheated or saturated. So for this we are using saturated steam table. So from saturated steam table at pressure P1 is equal to 70 bar. Saturation temperature is equal to 285.8 degrees centigrade and the temperature given to us is 500 degrees, which is more than TS. Is temperature given to us is 500 degrees centigrade, which is greater than saturation temperature 285.8 degrees centigrade. So the steam is initially superheated because temperature given to us is more than saturation point. So TS diagram for this is temperature in degree centigrade and entropy in kilojoule per kilogram per Kelvin. This is saturation curve. Initially steam is superheated and finally in real process entropy in real or actual process entropy increases from S1 to S2. In an ideal process entropy will be constant. So this is straight line constant entropy process. This is ideal reversible process. And this dashed line is a real and irreversible process. and we know that entropy will be either constant or increases. So for ideal reversible process, we know that entropy is constant and change in entropy will be equal to 0. And in real and irreversible, entropy increases from 1 to 2. This is S2 and this is S1. This is S1 is equal to S2S. At this point, S1 is equal to S2S. This is reversible process, and this process S2. This is S2 which is greater than S1. So entropy will be equal to 0 or entropy will be greater than 0. These are the two cases. There is no concept of decrease of entropy. So entropy is greater than, change in entropy is greater than or equal to 0. So this is the TS diagram for the process, adiabatic process. So we know that isentropic efficiency is equal to H1 minus H2 divided by H1 minus H2S. First we will find H1, H2 and H2S. So H1 is in superheated region. From TS diagram we know that H1 is in superheated region. So from superheated steam table at pressure P1 is equal to 70 bar and temperature T1 is equal to 500 degrees centigrade. H1 is equal to 3410 kilojoule per kg and S1 is equal to 6.796 kilojoule per kilogram. And now we found H2. So H2 is unsaturated vapor line. H2 is, this is H2 unsaturated vapor line. So from saturated steam table at pressure P2 is equal to 2 bar. H2 is equal to Hg saturated vapor line, which is equal to 2707 kilojoule per kilogram. This is scale 1 S1, and S2 is equal to 7.127 kilojoule per kilogram per Kelvin. Now to find H2S. H2S is in wet region. This is H2S. H2S is in wet region. So for H2S, first we find X2S. So as H2S is in wet region, so for H2S, first we find X2S. So for H2S we use entropy equation, because from TS diagram S1 is equal to S2S. This is from TS diagram. From TS diagram S1 is equal to S2S. This is TS diagram and this is constant entropy line. So for this we use equation S2S is equal to SF2S plus X2S into SG2S minus SF2S. And to find H2S we are using equation H2S is equal to HF2S plus X2S into HG2S minus HF2S. So first we find SF, SG, HF and HG from steam table. So from saturated steam table at pressure P2, at point 2 pressure is 2 bar. SF2S is equal to SF2S is equal to 1.530 kilojoule per kilogram per Kelvin, and Sg2S is equal to 7.127 kilojoule per kilogram per Kelvin, and HF2S is equal to 505 kilojoule per kilogram per Kelvin, and HF2S is equal to Hg2S 2707 kilojoule per kilogram per Kelvin. Now to find X2S, use equation S2S is equal to SF2S plus X2S and to Sg2S minus SF2S. Putting values in this equation, S2S is equal to 6.796 kilojoule per kilogram per Kelvin is equal to SF2S. SF2S is equal to 1.530 kilojoule per kilogram per Kelvin. We have to find X2S, and Sg2S is equal to 7.127 kilojoule per kilogram per Kelvin minus HF2S is equal to SF2S is equal to 1.530 kilojoule per kilogram per Kelvin. Now this is simple equation. All things are known, only X2S is unknown. So simplify this equation, rearrange and simplify this equation, and find X2S, which is equal to 0.9409. Now you can find H2S. A formula for H2S is equal to HF plus X2S Hg2S minus HF2S. Putting values in this equation, HF2S is equal to 505 kilojoule per kg plus X2S is equal to 0.9409. Hg2S is equal to 2707 kilojoule per kg minus 505 kilojoule per kg. This is simple calculation. Calculate this and find the value of H2S, which is equal to 2576.8 kilojoule per kg. Now find isentropic efficiency. So isentropic efficiency is equal to H1 minus H2 divided by H1 minus H2S. H1 is equal to 3410 minus 2707 kilojoule per kg, and H1 minus H2S is equal to 3410 minus 2576.6 kilojoule per kg. Units are same in numerator and denominator, and isentropic efficiency is equal to 0. Simplify this, so the answer will be 0.844, and in percentage multiply by 100 and divide by 100. So divide by 100 mean percent. So isentropic efficiency is equal to 84.4%. Now we have to find effectiveness. So effectiveness is equal to increase in exergy of surrounding increase in exergy of surrounding divided by loss in exergy of the system. Loss in exergy of the system. So increase in exergy of system is equal to H1 minus H2, and loss in exergy of system is H1 minus H2 minus T naught into S1 minus S2. All the values are known to us, so far just putting the values. H1 is equal to 3410 kilojoule per kg minus H2 is equal to 2707 kilojoule per kg divided by H1 minus H2. H1 is 3410 kilojoule per kg minus H2 is equal to 2707 kilojoule per kg minus T naught is 17 degrees centigrade, and in Kelvin this is equal to 17 plus 273 which into Kelvin, which is equal to 290 Kelvin. So this is equal to 29. This is atmospheric temperature. And S1 minus S2. S1 is equal to 6.796 minus S2 is equal to 7.127, and unit is kilojoule per kilogram per Kelvin. This Kelvin will be cancelled with Kelvin. So 3410 minus 2707 is equal to 703 kilojoule per kilogram divided by 703 kilojoule per kilogram minus, and 6.796 minus 7.127 and to multiply by 290 is equal to minus 95.99 kilojoule per kg. So this minus multiplication is equal to plus, so this is equal to 703 kilojoule per kg divided by 703 kilojoule per kg minus is equal to plus 95.99 kilojoule per kg. So further simplify, this final answer will be equal to 0.88, and in percent multiply and divide by 100. Divide by 100 is equal to percent. So final effectiveness value will be equal to 88%. So this is the video of effectiveness, and for more videos please like and subscribe my YouTube channel. Thank you.